So Christmas is almost upon us, which means it's time that we do a Christmas project. So what we've got here are some Christmas baubles which are going to hang on the Christmas tree with some LEDs scattered around the board. So this is a black PCB with the immersion gold finish, and I often get asked why I choose the immersion gold finish, and the main reason is that the PCBs store a lot better. So less applicable on this particular design, but on other PCBs, you may not want to assemble all the boards in one go. So you could come back a year's time, or maybe even 2 years' time, and still solder these boards absolutely fine, where some of the other finishes can be more difficult to work with at some later period in time. So that's the main reason. The other one is that components sit very flat on the PCB. So when you're hand assembling it in particular, it can be quite useful to have that very flat surface, especially on multi-pin devices. So what we're going to do today is we're going to build up these boards. I've got a stencil ordered and hopefully we'll be able to apply it to the board quite easily. Let's have a little look at the schematic so we can work out what's going on. The main design intent for this PCB is to have an array of LEDs scattered around the board. So you can see we've got the LEDs that are going to be poking through holes all over the board, and we're going to create some nice animated effects with the LEDs on the PCB. Now that's pretty straightforward, but there were some usability issues which I was concerned about when designing the board. Mainly, I want this to be battery operated, so we haven't got wires linking all of the boards up. But then how do you go about turning the boards on and off? Because you're not really going to want to go around and turn on 10 or 12 PCBs on the Christmas tree every day or whenever you're going to have the Christmas lights on. So what I've actually done is I've added in some additional features onto the board. So let's have a little look at those. So we've got our usual stuff for supporting the microcontroller. So we've got our programming header so that we can program the PIC once it's soldered onto the board. We've got our battery supply. So this is supplied with a CR2032 coin cell. And these coin cells aren't really designed for high current use, and even just driving some LEDs at a couple of milliamp is abusing that battery quite heavily and doesn't allow you to necessarily get all of the energy out of the battery. So what I've got here is a bank of ceramic capacitors to try and smooth out the peaks in supply so that the battery isn't seeing quite so much peak current draw. Then we've got our PIC, which is a PIC 24F with various low power modes so that this device can go into a sleep mode and not draw too much power from the coin cell. Then we've got our mode switch, which is just a standard tactile switch so that we can change the pattern of the LEDs. And then we've got the potentially more interesting part of the design. So I decided the best way to determine when to start flashing the LEDs was based on the sound level in the room. So if it's completely silent, the LEDs will stop flashing. As soon as some sound is detected from a TV or people talking, the LEDs will start flashing and they'll continue to flash for some period of time after silence is detected. So we're basing this around a MEMS electret microphone. It's a little 4-pin BGA device, so that's this part here. And that already has the biasing circuitry and the buffer built in. We then AC couple that into this amplifier here, which then feeds into the ADC on the microcontroller. And what we're doing is, on the microcontroller, it's generally going to stay in sleep mode, and then every time it's woken up by the watchdog timer, so that's once every 8 seconds or so, it's going to apply power to this node here to power all of this circuitry up, and then it's going to measure the sound signal. If it's below the threshold, then it goes back to sleep and powers all this down. Otherwise, it starts flashing the LEDs. So it's AC coupled into this amplifier, and then we're biasing this rail at half of the supply voltage so that our AC sound signal is centered around the mid voltage point so that the signal is fully in range of the ADC on the board. The half rail is set by these two resistors here, and in this instance I fed it through this buffer, but the circuit is very slightly different to the circuit that I implemented on the PCB, and it turns out that this buffer isn't needed because we're actually ending up feeding it through this 100k resistor into this node, so the buffer's not really doing any useful function at all. Then we've got this amplifier circuit here, and then we've got a network of resistors and capacitors here to amplify and also to roll off the amplification at a certain frequency so that we don't exceed the gain bandwidth product of the op amp, but also so that we don't end up with aliasing effects. And there is a trade-off between the value of these resistors and capacitors. When we power up the circuit, this capacitor takes quite some time to reach that steady state voltage. And all the time that we're waiting for that capacitor to charge, we can't take any readings from the signal, so we're just burning power in with the clock running and with all of this circuitry powered up. The trade-off is that if we start changing these resistors so that the capacitor reaches steady state quicker, we don't get so much gain. The other trade-off is that the cutoff point of the low-pass filter starts increasing, and actually R5 and C9 form a high-pass filter. We've got a low-pass filter here, but the high-pass, if we start decreasing the value of C9 so that the startup doesn't take so long, the side effect is we don't pick up the low frequencies, and those are generally the frequencies that are easier for us to detect in the software. So there's a bit of a trade-off to have, and I actually created a big Excel spreadsheet. This is the main output from it, and it basically says that our optimal values are going to be 1 meg for R3, 1.5k for R5, which gives us a gain of 666. Our capacitor is at 1 microfarad, which means that our cutoff point is at 1 kilohertz. So below 1 kilohertz, we're starting not to detect that. And then we've got our 100 picofarad and 1 meg resistor for forming the low pass filter. And one of the things to note about these ultra low power op amps is they do have quite a low gain bandwidth product because they are very low power op amps. So we do have to make sure that we design this circuitry so that we're within the parameters of the op amp. And with relatively high gains like this, we are limited as to the frequency band that we're going to be able to listen to. So these are the optimal values that I've come up with. C9 does require a little bit of modification on the PCB for us to mount that, because I had this originally connected to this mid-rail point. It turns out that I'd made a mistake and I'd sort of mixed up two circuits in my head while I was designing the circuit, and we do have to bodge these two components slightly on the PCB. Hopefully you managed to follow all that. I'm not sure if I explained it quite as well as I could have done, but there's actually quite a lot going on with this relatively straightforward bit of electronics, so quite a lot of trade-offs to make. And that's where simulations and Excel spreadsheets are really helpful for making those design decisions. In terms of LEDs, what we're using are these LEDs from LCSC, and they're little surface mount LEDs that actually mount through the PCB. So you can see we've got the pads on one side of the board with their hole, and then the LED actually sits in that hole and pokes through on the other side. So these are white LEDs. You can get them in all different types of colours, but they're through PCB surface mount LEDs. So I didn't have to bother with surface mounting components on this side of the board, which is notionally completely clear of components. So what we're going to do is start assembling these boards up, then we can put the firmware on and have a look at the operation. So I think this is about as good as we can do to hold the PCBs in place. It's a little bit difficult with the circular boards, but we've got our stencil that we can now fold on top, and then we can apply the paste and then take it out and put the next PCB in. Right, so there's 12 PCBs ready to be reflowed, and this is where a reflow oven would have been really useful, but instead we're going to have to heat the boards up and use the hot air gun. Right, so next up we need to make the modification to the PCB where I made a mistake on here. We need to fit a resistor and then a capacitor to the ground plane. So I'm going to scrape away a bit of the ground plane just here. And then we'll just clean up with some alcohol just to remove the remnants of the solder mask. And then we'll put a few blobs of solder paste down for the capacitor. And there we go. And now with assembly complete, we can program up all of the PCBs. Right, and so after putting the coin cells in most of these, they seem to be working properly. So after a few seconds of talking, we see the sort of snowfall effect. I've got 3 PCBs at the top here that don't seem to be doing anything, so I need to have a little look at those. But in terms of these ones that are working, we can press the mode button on the back, and it will change the pattern slightly. You can see that's a slightly different pattern to the sort of snowfall effect that the others have got. If we press it again we've got a slightly different pattern. And there's probably a few others that I could come up with, but actually I quite like the snowfall type effect that's illustrated here. So I think that's a really nice effect with the LEDs, but it's a pretty boring PCB and doesn't look very Christmassy. So what I've done is I've gone and designed another board to mount on top of it with the cutout for the LEDs. And this is a white PCB with the hot air solder level finish cut away to create these nice snowflake effects. But even still, I think we can go one better. And what I've done is I've designed another board to sit on top to give it a kind of 3D effect. So this time we've gone back to the black PCB, and this one's got the immersion gold finish saying Merry Christmas. And I think that looks really quite nice. And we've got a little bit of depth to the PCB by having the layer stack. I could have designed the electronics to go on the white board, but I did sort of want the black at the front and then black at the back, so it wouldn't have worked. I wouldn't have been able to have the black colour on the back of the white circuit board. So I'm going to glue these together, and that's basically the final effect. So to glue them together, we're going to try using some super glue, and we're going to use the activator as well as the super glue itself. So these are made by Everbuild, and just give the PCB a quick spray like that and wait for that to dry a little bit. And while that's going on, what we do is we just apply some super glue to this PCB in a few select areas, and then we can just place this PCB on top, make sure it's all lined up properly. And the super glue activator causes the super glue to set really quickly, so we just need to hold it together for about 30 seconds or so, and then this should be glued very tightly. Yeah, so that appears to be glued now. So what we're going to do is then give this PCB a little spray, and then we're going to put some super glue on the back of this board, and then just leave that again for 30 seconds or so. I'm going to repeat that on all of these other boards. So I think overall we've got a really stylish looking Christmas decoration here. By cutting away the solder mask, we've got some really nice shiny parts to the design, and all of the artwork was designed in Adobe Illustrator, and there were a few challenges with working out quite how much to cut away from the top PCB, because the 1mm router cutter did put some restrictions on what we could achieve. But I think overall, I think we've come up with quite a good result. And overall, I think it looks quite professional, quite unique. I've not seen anything like this before. It's a shame about the little bodge with the resistor and capacitor, but this was the first spin of the PCB, and there's probably a few things that I would change in a future design. In the next few weeks, I'll probably upload a video on the low power design aspects of designing something like this, because there were quite a few thoughts into how to maximize the battery life, and actually this should last quite a long time. So even if it's activated for quite a few hours per day, we could leave the battery in and it would happily last probably 3 Christmases or so. So, we're really getting a decent amount of battery life out of these little coin cells, partly due to the way that I'm multiplexing the LEDs using one PWM generator on the microcontroller, but also turning off parts when we don't need them and using the watchdog timer to keep it in sleep mode as long as possible, do mean that we get really long battery life. So I'm going to cover that in a future video, but until next time, thanks for watching.